In the beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
It sounds like a Hollywood blockbuster. A deadly asteroid is on a collision course with Earth. But in reality, is there a giant doomsday rock that threatens to wipe out civilization?
It's not a question of if it'll happen, it's a question of when it will happen.
An asteroid took out the dinosaurs 65 million years ago. Are we next? Go in search of these cosmic killers, assess their threat, and analyze the best ways to get them before they get us. Stopping Armageddon starts now. It came from somewhere in the asteroid belt between Mars and Jupiter. A massive pile of rock and rubble, rotating and rumbling its way towards Earth. What was once mere debris from the Big Bang is now destined to make a Big Bang of its own. Bursting through the Earth's atmosphere, this giant asteroid becomes an unstoppable force. Nearly 2 million times more powerful than the Soviet Emperor bomb, the largest, most powerful explosive device ever detonated. Its target, Los Angeles. The last thing anyone there sees is a flash, a fireball, and then
if this asteroid were as large as we might imagine, a 10-kilometer asteroid, we would be talking about a crater that is 10 times larger than that. So we'd be talking about a 50-mile crater. So all of Los Angeles would end up being this humongous crater. We'd be talking about absolute devastation, nothing left over, range up to perhaps 100 miles. As far away as San Diego, they would get massive earthquakes, they would get massive air blasts, winds that would simply flatten everything 200 miles away, would kill everything out to a range of perhaps 1,000 miles.
And that's just the immediate impact.
Then you would have all this debris fall back on the planet Earth. It'd be like a Christmas tree, seeing all these ornaments being thrown out in all directions. And then you would see firestorms, enormous areas of the planet Earth burning, releasing even more soot and ash in the air. Blanketing out sunlight, temperatures would then plunge, and life itself would be perhaps extinguished.
What you've just seen is a worst-case scenario of a major Earth impact event.
The kinds of asteroids that can extinguish much of the life on Earth, most of the species, come around every, say, 100 million years or so. And it's not a periodic phenomenon. It doesn't happen every 100 million years. It could happen at any time, just on average, roughly once every 100 million years. So it's not a question of if it'll happen. It's a question of when it will happen.
Asteroids and comets have been crashing into the Earth for as long as there's been an Earth. Soon after its formation, about 4.5 billion years ago, our planet became a frequent target in a cosmic shooting gallery.
Asteroids and comets brought to the early Earth much of the organic materials and water that allowed life to form. Subsequent collisions, like the one that took out the dinosaurs 65 million years ago, punctuated evolution, allowing the most adaptable species, that's us, to rise to the top of the food chain. So we owe our very existence and our position to these objects that sometimes cause a threat.
According to the Earth Impact Database, more than 160 impact craters have been identified. The largest one is called Chicxulub, Mayan for Tail of the Devil. This crater measures more than 110 miles in diameter. It was made by the asteroid that took out the dinosaurs when it crashed off Mexico's Yucatan Peninsula. Closer to home, the database also includes Meteor Crater in northern Arizona. Now a tourist attraction, this kilometer-wide hole was left by a huge chunk of cosmic iron ore that collided with Earth about 50,000 years ago. Much more recently, an enormous near-Earth object didn't leave a crater, but still made quite an impression. Packing the energy of a 15-megaton bomb, more than 1,000 times that of the one dropped on Hiroshima, it exploded over Tunguska, Siberia in 1908.
It didn't even hit the ground, but the shock wave from this airburst flattened all the trees and vegetation in the area. It was like a gigantic hand that came down from the heavens to press all the forests and trees. That's the size of the devastation of Tunguska.
If the Tunguska event had occurred over Moscow or New York or Los Angeles, the devastation would have been catastrophic, completely destroying the city and a vast area around it.
Though the chances of a Tunguska-type event happening again are remote, perhaps once every 500 years, the potential for a major disaster, if it does occur, can't be ignored. That's why NASA established the Near-Earth Object Program at the Jet Propulsion Laboratory. Its mission is to find asteroids that pose the most serious threats to Earth. The first step in stopping Armageddon.
2032 is 0.02.
These are just nominals.
There's a 0.01.
Whenever I'm asked what are the most important aspects of the Near-Earth Object Program, I say, well, the three most important aspects are find them early, and then find them early. Because if we can find them 10, 20, 30 years in advance of a problem, we have the technology now to mitigate them.
The NEO program employs 5 full-time telescopes located across the American Southwest and around the world. They search the skies for asteroids, especially those measuring at least 1 kilometer in diameter, or about 2/3 of a mile and larger. Asteroids that big can cause worldwide devastation on impact.
We can compare the process of finding asteroids to the process of figuring out where a golf ball is going to land after it's been hit. Now just imagine that instead of being able to see the golf ball continuously throughout its entire flight, I only have a handful of freeze-frame snapshots of it while it's moving. And now I've got to figure out where it's going to go. So first of all, I've got to correctly distinguish the golf ball in the frame from all other objects in the frame, say trees or birds, or even other golf balls that may not be the same one. Once I've identified the golf ball in each of the frames, I need to use what I know about the laws of gravity to correctly fit a trajectory to it so that I can figure out where it finally lands. In the same way, when we look for asteroids, we have to just take snapshots of different parts of the sky and distinguish the asteroid from stars, from galaxies, and from any other transient phenomenon like, say, cosmic rays. Then we have to use the laws of gravity to fit a model orbit to it and figure out where it's actually going to go in the end.
No telescopes in the NEO program have found more asteroids than those at Lincoln Near-Earth Asteroid Research, Linear for short. Located in southern New Mexico, they've discovered almost half of the 5,000 known near-Earth asteroids, including about half of the 700 objects measuring 1 kilometer or larger.
One of the telescopes we use for hunting for asteroids with the Linear program is behind me. This is actually not a rather large telescope by astronomical standards. It's 1 meter in aperture, but the secret to its sensitivity is that blue square that you can see down in the bottom of the telescope. That's a charge-coupled device specially manufactured for wide area sensitive search. And the combination of this telescope and that CCD gives us a system exceeding 1 million times the sensitivity of a human eye. This is what the sky looks like through the Linear telescope. What you can see is a number of stars here that are fixed, and also in that data there are a number of near-Earth objects. What I'm going to do now is have the process the data and analyze it to find the moving objects. What it's doing is it's clicking through the 5 frames, and in fact has now discovered a number of moving objects. What you see here are ones that look like this. These are actually main belt asteroids. They're out located in the main belt between Mars and Jupiter. They don't pose any threat at all. On the other hand, you find a couple of them that are very different. This one's in fact going opposite motion of the main belt and much, much faster. This one's going straight across. These are in fact near-Earth objects, and in fact these are 2 that Linear discovered.
Linear sends its data to the Minor Planet Center in Cambridge, Massachusetts, the clearinghouse for all near-Earth object searches.
The Minor Planet Center's job specifically is to tie the observations of new NEOs with already existing NEOs and just refine the orbits of the near-Earth objects in general. And with the orbits, other groups can go perform physical observations using various telescopes to determine the actual sizes of the objects.
The Minor Planet Center considers an asteroid potentially hazardous if its orbit brings it to within 5 million miles of Earth. That's too close for cosmic comfort, and definitely earns a rating on the Torino scale, a guide scientists use to assess the threat level posed by an asteroid.
This scale ranges from 0 to 10, where 10 is absolute destruction, and 0 means no hazard at all, or very little chance of any sort of impact. The highest rating that any object has ever received so far on the Torino scale was an asteroid called Apophis. And Apophis is named after the Egyptian god of destruction. So Apophis at one point had a Torino rating as high as 4.
In fact, in the weeks following its discovery in December 2004, there was a time period when it appeared to have as high as a 2.7% chance of impact in 2029. That's about 1 in 37. These are roulette odds, not lottery odds. And so at that time, everybody really started paying close attention to Apophis as a possible threat in 2029.
Measuring about 270 meters in length, or more than 800 feet, Apophis has the energy of a 500 megaton bomb, enough to wipe out a major city or cause a devastating tsunami. In 2029, Apophis will come closer to Earth than the satellite bringing you this TV program. Despite the unusual proximity, additional radar and optical analysis have eliminated the threat of an Earth impact, a 0 on the Torino scale. But during that orbit, Apophis may pass through a keyhole, an area in space where if the asteroid passes through it, there's a 1 in 45,000 chance of another encounter with Earth in 2036.
The possibility of a collision in 2036 is something that we're very carefully monitoring, and yet we have excellent opportunities to observe Apophis in around the year 2013 and again around the year 2021, at which time, with very high confidence, we can say that that possibility of impact will be eliminated. In the unlikely case that that possibility of impact persists, we'll still have plenty of time to avert the collision through some kind of a mitigation campaign.
Mitigation is the next step to stopping Armageddon. How do we prevent Apophis or any large asteroid from colliding into Earth and causing mass devastation? The obvious answer may be the worst option of all. Our very survival depends on the answer to this question. If we find a large asteroid on track to collide with Earth, can we do anything to prevent it from happening?
You can think of an asteroid impact as a huge natural disaster. But the thing that makes this different than the kinds of natural disasters that we know about, hurricanes or earthquakes and things like that, is that in principle it's preventable. So your job isn't necessarily how do you clean up in the aftermath, but how do you prevent it? And that's an important distinction.
Preventing a massive Earth impact brings us to step 2 for stopping Armageddon: mitigation. Neutralizing a deadly near-Earth object is no easy task. Take it from Hollywood. Or maybe not.
The worst thing to do is to look at all the Hollywood movies where we have Macho Man going out in the space shuttle, way out in deep space, planting hydrogen bombs on these objects. Well, first of all, the space shuttle can't even reach those distances. The space shuttle simply goes around the planet Earth itself. Second of all, and more important, to blow up an asteroid is the worst possible scenario. Because instead of having one monster asteroid, you now have 2, 3, 4 pieces, each piece capable of initiating tremendous havoc on the planet Earth.
On the other hand, if it were a large object and you had enough time, several years, you could try and blow it up and hope that the shrapnel would miss the Earth, or most of it would. But large objects we almost certainly would find ahead of time. It's really the small, far more numerous objects that are the ones that are tough to deal with.
If outright destruction, such as a Hollywood-style bombing, is too risky, or at best reserved for only the largest asteroids, there's a safer way to move a near-Earth object out of harm's way, and that's by deflection.
If an asteroid is headed toward an impact with Earth, you're far better off by changing its orbit very slightly so that it misses the Earth, but stays in one piece, much better off than you are trying to break it up. I mean, you can't make anything disappear, you simply break it into pieces. Bombing it is going to break it into pieces, which could do much more damage. It's a shotgun blast instead of a rifle bullet.
To work best, deflection requires as much lead time as possible, years, if not decades. Put simply, early detection means early deflection.
More importantly, the farther away it is, the less force we have to apply in order to cause a large shift in the asteroid's orbit.
To demonstrate the point, let's play hockey. The further away from the net a player shoots the puck, the less deflection will be needed to prevent a goal. However, if a player takes a shot much closer to the net, then a much larger deflection is required to keep the puck from going in. Now imagine that the puck is an asteroid and the net is the Earth.
The preferred scenarios are to deflect the asteroid by changing its velocity. If we can do that sufficiently far in advance, for example, 10 years, we only need to change its velocity less than 1 centimeter per second. So it's very, very small change in velocity. The cumulative effect then will mean that it will get to where we are either before we are there or after the Earth is at that position, so it is no longer a problem.
To do just that, several deflection strategies have been proposed. And with apologies to Bruce Willis, none requires a manned mission.
In fact, a manned mission would significantly hinder these things. To this point, with current technology and current vehicles, we can't really get very far away from the Earth. And that severely constrains your ability to actually solve one of these problems when the optimal time might be the opposite side of the sun to meet the asteroid.
The thing is deployed.
One deflection strategy advanced by French researchers calls for commandeering a non-threatening asteroid to knock an Earth-bound object off course. Call this strategy asteroid versus asteroid.
It's not totally outside the realm of possibility. Trying to park it where we want it and not have it hit the Earth is in itself questionable. We have only a certain number of these that are anywhere near the Earth. And finding one that could be easily moved in near Earth, obviously you're talking about the same asteroids, it might be danger of hitting the Earth to start with. And so I would not be in favor of thinking of bringing one in to have it later. And the ability to shoot a large asteroid later is very difficult. We don't need something that large to have enough energy and momentum to deflect it.
Another proposal comes from the European Space Agency. It's preparing designs for a mission named Don Quixote. Instead of tilting at windmills, the agency plans to alter the course of a non-threatening asteroid by launching a spacecraft called a kinetic impactor to collide into it.
A kinetic impactor is number one in my toolbox of what I would do. It's very simple, it's straightforward, and we at least have a bottom line, a minimum effect that we know we can count on. We can launch something large enough at sufficiently high velocity within at least, let's say, 10 years, 20 years, to deflect an asteroid up into the several hundred-meter range.
Kinetic impact and asteroid versus asteroid strategies require a massive collision to deflect a threatening near-Earth object. But other proposals suggest it may be possible to stop Armageddon with nothing more than a beam of light. There are several ways to stop Armageddon. Some propose a sudden, massive impact that literally knocks an Earth-bound asteroid off course. Others suggest the mission can be accomplished without a collision by using other means, such as a standoff nuclear explosion, to push the asteroid out of harm's way.
You detonate the weapon some small distance off the surface. The main effect then is for energy, hopefully in the form of neutrons, penetrating the surface, and you heat it and you blow off pieces of the surface. It's over a fairly large area, so you diminish the chance of breaking it up.
There's one problem, though. Nukes are banned from space by international treaty. But if an asteroid threatens our very survival, will that really matter?
In terms of mitigation strategies, I'm most impressed with the use of the nuclear weapons. And I think it's the most efficient. Sure, it's not been tested, but neither has anything else that we have. And also, just from a personal standpoint, I would much rather deflect an object than sacrifice North America. And if I had to go to court afterwards, that would be just fine with me.
But you don't have to nuke an asteroid in order to nudge it. Safer methods include using solar sails. These orbiting reflectors, according to advocates, could concentrate the sun's rays on an asteroid. The heat generated would vaporize surface rock, creating a jet of material that would propel the object away from an Earthbound trajectory. Then there are lasers. If they're powerful enough to cut the strongest metal and perform delicate surgeries, then maybe a more powerful version could deflect an asteroid.
The laser is very attractive because it's more economical. It costs less, basically. It's easier to do. It could be a robotic spacecraft. The laser uses a beam of light to the asteroid, which causes material to fly off from the asteroid, which then pushes the asteroid. You don't have to carry the material up there that's going to exert the force on the asteroid. The laser can be very precisely directed. It's very gradual. It can be done over a 3-month period.
Researchers discovered a laser's potential by accident in the 80s while experimenting with short pulses on a wafer made of silicon, material similar to the surface of an asteroid.
We basically set up a movie camera and timed it with a laser so we could take step action shots of the material leaving the surface of the silicon wafer. And we were surprised to discover what we found. That is, we can actually see these chunks of material coming off and see them vaporize. It was a scientific discovery as well as a new technology.
As significant as that discovery was, it's still a big leap from a silicon wafer to an asteroid. But it's one that can be made, proponents claim, with a laser pulse 5,000 times more powerful than those we use every day on Earth. This super laser, powered by existing rockets and solar panels, could park as many as 5 kilometers away from an asteroid, then use a series of short pulses rather than a continuous one to deflect it.
The reason for the pulse is that the very short pulse can deliver enough intensity to the surface of the asteroid so that the material explodes off from the asteroid. When that material explodes off from the asteroid, it pushes the asteroid in the direction that you want to send it. You also need the very short pulse because as the laser pulse strikes the surface of the asteroid, it creates a cloud of material that emerges from the asteroid. That cloud of material will absorb any additional light that's sent to the asteroid. So it's extremely important to get all of the light energy into that area of the asteroid in that very short time before that black cloud forms.
To some experts, lasers and even solar sails could work, at least in principle. The intense light they both emit is adjustable and adaptable to all types of asteroids, and the ejected material, mere puffs of dust, would pose no threat to Earth. But their potential drawbacks could prove prohibitive.
Keeping the laser source or a large solar mirror in the correct place is very difficult to do and has to be done for a long time. With regard to the solar reflection also, then there's a question of the dust that's blown out. What is it going to do to the solar mirror? And so there are significant long-term problems. And so whether that could be done in the future, we don't know. At the present time, it's certainly outside of our capability.
There are continuous lasers now that produce more power, 25 kilowatts, 50 kilowatts, that have been made for military purposes that have more power than is necessary. The kind that we're proposing would require taking the ultra-short pulse lasers and increasing the power up to at least 5 kilowatts, maybe 10 kilowatts. A focused effort could probably do this within 5 to 10 years, could actually be done if there was an intent to do so.
And why stop at just one laser? One day, a fleet of them could be permanently stationed around Earth to act as a defensive shield against asteroids that threaten us.
It would avoid the danger of having a last-minute scramble to solve the problem and having to send up nuclear devices, nuclear weapons into space, trying to blow up the asteroid, which is probably a bad idea.
Lasers show potential as asteroid deflectors, but it'll be a long time before they're a viable option. Until then, there's another mitigation proposal that deserves serious attention. It's the brainchild of two former astronauts who insist it's the only real way to stop Armageddon. Of all the proposals to stop Armageddon, the most effective one may be a contraption called a gravity tractor. For such a complicated undertaking, it operates on a very simple principle.
We know that everything out there in space has a gravitational pull. So asteroids themselves have a gravitational pull. And we also know that a spaceship interacts gravitationally with the asteroid. So if the spaceship were to come close enough to the asteroid, it could then begin to attract the asteroid slowly out of its course, if we can get it in time.
Developed by the B612 Foundation, named after the asteroid in the literary classic The Little Prince, the gravity tractor is gaining popularity due to the efforts of its chief advocates, two former astronauts, Ed Lu and Rusty Schweikert.
The gravity tractor is a very weak deflection concept, but it's very precise. And so we don't recommend using it for what we call the primary deflection. That is, to make the asteroid miss the Earth. But once you've done that with a kinetic impact, which is a very imprecise maneuver, then you come in with the gravitational tractor and you make a very precision adjustment on what you've done with the primary deflection.
The gravity tractor is one of the very few asteroid deflection mechanisms that is in any way realistic. The only two that are probably realistic right now are kinetic impactor, where you just basically run into the asteroid with a spacecraft, or the gravity tractor. Apart from those two, most of the rest of those are pretty much science fiction.
Using mostly existing technology and powered by a combination of ion engines and solar panels, the gravity tractor itself is about the size and weight of a golf cart. Not very large by spacecraft standards, but it's still big enough, according to its proponents, to finish the job after a kinetic impact.
This asteroid is spinning around an axis or tumbling, whatever, and I come up with the gravity tractor and I basically park here. I want to pull it in that direction. So in spite of the fact that it's tumbling, I don't ever touch it. I just pull up in front of it, if that's the direction I want to pull it, and I just stay there while it's tumbling. Let's say if the asteroid itself is 300 feet in diameter, then we would want to hover something like 250 feet from the center of gravity of that asteroid. In other words, about 1.5 radiuses out from that tumbling asteroid. I don't let the gravity of the asteroid pull me in. I have to fire my ion engine thrusters off to the side so I don't blast it. And by doing that, I stay right there for a week, a month, a year, whatever it takes. Ion engines go for long, long periods of time. And now, because I have a radio transponder in my gravity tractor, the Earth can track me very precisely, and I know exactly the change in the orbit that I've made to the asteroid itself. You're reshaping the solar system without ever touching anything.
That ability to make controlled, precise movements is the gravity tractor's chief asset.
What you need to do is make sure that after you've deflected any asteroid, that it doesn't come back and hit you at a later point. What a gravity tractor allows you to do is to measure precisely exactly where it's going and to make tiny corrections to it so that you are very certain that it is not going to come back and hit you.
Despite this advantage, the gravity tractor's major drawback is its very small force. Maybe too small to make a difference on a really big asteroid.
The gravity tractor takes a long time and a small asteroid to be effective. It would have to be much smaller than 1 kilometer, perhaps 150 meters, 300 meters, something on the size of Apophis or smaller. If we're talking about a need for a larger asteroid and we don't have as much time to devote to it, then gravity tractor is probably not the method of choice.
But it turns out that the expected time between when you find that an asteroid impact is possible and when the actual impact is going to happen is many decades. So most of the time, you have time to use such a thing.
By the time we get hit by something that big, we're going to have technology we can't even imagine now. So there'll be something else and not the gravity tractor. But if we had to do it now, we could do it. The point is that we can protect the Earth right now from asteroid impacts if we do our work.
To demonstrate the gravity tractor's effectiveness, the B612 Foundation aims to perform a test deflection on a non-threatening asteroid by the year 2015.
That's really important because if we find an asteroid that's uncomfortably close to hitting the Earth and you decide that you have to deflect it, that's not a good time for your test flight. You want the test flight to be done beforehand so you work out any possible bugs.
The real trick is convincing NASA that it ought to demonstrate this capability before we end up having to use it. That's the problem. You're dealing with potentially millions of lives. It's simple and cheap to demonstrate it. So let's demonstrate it, and then we know.
This leads to the third and final step in stopping Armageddon. Who decides when and what to do if an asteroid has our name on it? There are 3 fundamental steps to stopping Armageddon. Detection and mitigation comprise the first 2. The third, and maybe most challenging one of all, is who makes the decision when to act.
Right now, if we knew something were coming, I think it's likely that we would run around and not do anything in time. I think it's important to have basically sort of the manual. When the asteroid comes, what do we do?
Answering this question gains urgency as bigger and better telescopes come online, such as PAN-STARRS, an acronym for Panoramic Survey Telescope and Rapid Response System.
PAN-STARRS is a University of Hawaii project that may well revolutionize the search for near-Earth objects. The idea is to have a very wide field telescope with a huge field of view, and so they can go deeper, that is further out in space, and do it faster and cover much more of the sky every night. New programs like PAN-STARRS are going to increase the discovery rate, and so once we find the vast majority of these objects, we can easily track them 100 years into the future and see whether or not any of them are a problem.
Some experts predict that within the next 10 to 20 years, as many as 1 million near-Earth objects could be discovered. That's in addition to the more than 5,000 we've already found. Even with this exponential increase, it's still possible that a space object, perhaps a comet, could evade detection and hit us.
Comets can literally come out of the blue. They come from the outer reaches of the solar system, and they come in, and we may only have a few years or less to mount some kind of a deflection effort. So we don't know for sure that there's no comet heading our way. But comets don't fly by the Earth very much, and so we have a very good confidence that the predominant Earth hazard is coming from asteroids.
It is possible right now that we could be hit by an asteroid that we're unaware of. There are plenty of surveys going on right now, but they're geared for finding the 1 kilometer and larger asteroids. And so there are objects down to about 150 meters that we're particularly interested in, and we've only found a few % of those. So there needs to be much more surveying in the future to find those potentially hazardous objects.
Right now, there are no protocols about what to do, when to act, and who makes these decisions in the event of an imminent Earth impact. So who has the authority and the capability to protect the Earth?
NASA's current charter is to find them, track them, and physically characterize them. What are they made of? How are they put together? They don't yet have the charter to mitigate them. You can well imagine that an asteroid impact would be an international problem. So it's going to take some international cooperation to decide who does what and when.
International decisions are extremely slow. I think it's important that countries get together and talk about a protocol for how you would make such a decision. And if they begin their quibbling and arguing at the moment they find it, they may quibble and argue all of their time away before they have to do something.
The good news is this conceivably could unify the people of the world around something that affects all of us. And we could all work together to solve it.
The whole globe is at risk, not just any one country, and not just spacefaring nations. So while the spacefaring nations may end up with the responsibility to do something, who pays for it? Who says do it? Who handles the liability? We're working with the United Nations to get them prepared to make rapid decisions.
The Association of Space Explorers, an international organization of people who've flown in space, will submit recommendations for Earth impact preparedness to the United Nations in 2009. It's a first step. Until then, let these views serve as the best informed perspectives on the subject.
We need to think in terms of this is something that's important for Earth, it's important for the children, it's important for the people who come after us, and it's our willingness to prepare at this time and to give them the tools so that should the threat emerge later on, that there will be the resources and the ability and the knowledge to resolve that threat.
We may have another Tunguska, an event that is capable of wiping out an entire city, a city buster. However, on a scale of millions of years, perhaps 50 million years, we have the possibility of a life-extinguishing event. It's prudent to take efforts today because no one knows when the next impact will come. All we know is it's coming.
Strangely enough, I am not concerned about a potential impact in the near future. I know the probabilities. It is unlikely. But it is also unlikely that you will get on a plane and it will crash, and we still spend lots of money making planes safe. We have various ways of doing that. To me, this is almost an actuarial problem. We're going to determine what the threat is and prevent it.